homomorphic encryption, the first solution was introduced in 2009 by Craig Gentry at IBM, and it had been an open problem for about 30 years. And so that was a big breakthrough. But the proposal at that time was quite unusable and not really implementable, and certainly not efficient. So the first big step forward was an encryption scheme that was designed by a researcher in my team that was based on a different hard problem in mathematics that is very closely related to hard lattice problems. And so that was the first step. And then the second step was to make this system efficient. And there are a lot of different aspects of the problem that we worked on. Part of it was actually just changing the way that we encode information before we encrypt it. And that made a huge difference to start with. And I can give you more specifics on that if you'd be interested. So we take instead of encrypting the data bit by bit, taking a single bit and putting it into a single ciphertext, instead of doing that, we proposed using a lot of bits at once and encoding, using the bits as a representation for some large floating point number and encoding that directly into the polynomials as a representation of a floating point number. So then the polynomial could be encrypted, and then a ciphertext is actually representing an entire floating point number instead of representing a single bit. And it made it so that all the circuits that you have to evaluate were much more reasonable. They were completely compressed into one level. So you just have to do one multiplication of values instead of having a very deep circuit to do a simple multiplication. So that was a big innovation. Yes, and we had many other innovations that allow us to speed up the technology so that we are at the point we're at today. Another big contribution was using all kinds of number theoretic algorithms. So many of us that work in applied crypto are actually mathematicians by background, like myself. And so we use fast algorithms for polynomial multiplication to speed up encryption and operations on ciphertexts. There's also a huge engineering component of the work that we did to speed up the systems in software using better engineering practices and modern tools that are available, and now also projects that are targeted at hardware. So we have FPGA implementations and GPU implementations of homomorphic encryption that are orders of magnitude faster than just the software implementations. So you can implement homomorphic encryption in a way so that it is exactly the same as what would have happened on the unencrypted data. So no additional data loss. But what you have to balance is the kind of the performance versus the accuracy and the kind of approximation factor. The reality is that even on unencrypted data, there can be some data loss. If you're dealing with floating point numbers and only up to a certain amount of precision, as you compute, you are actually losing accuracy if you don't keep all of the extra digits. So that's true even on unencrypted data. But you can, on encrypted data, you can do the same thing, or you can use several innovations that make things more efficient. We actually have a new system proposed by researchers from Seoul National University, one of whom is on my team as a researcher now, and their system allows for approximate computation. So it makes it more efficient by always allowing to kind of lose a few digits of accuracy in order to keep going and be as efficient as possible. So that kind of trade-off is certainly worthwhile. And so, yes, we do tolerate some data loss, but as long as it's reasonable for whatever task we want to accomplish. Well, at the time I started this Women in Numbers Network in 2006 with two female colleagues in number theory. And the reason that we did it at the time was simple. We were very tired of going to number theory conferences where there were no women speakers or only one woman speaker, or I was the only one. And it was literally ridiculous because we all knew so many talented women in number theory. Why weren't they being invited to speak? So we decided to organize our own conference. And now it's grown into a huge worldwide effort. there are women in numbers in 20 different areas of mathematics, and I have a $1 million NSF grant which allows us to support networks through the AWM, and we are able to kind of grow these networks for women in many areas of research, and it translates into better numbers in terms of hiring and invitations at conferences and publications and all of that.